Okay, so we're going to look now at composition of functions and inverse of functions. You would have met compositions in school, but we'll do it again here. And inverses, you roughly would have had the idea in school as well. So this is about combining two functions together, where what you do is you take an input to the first function, produce its output, and then take that output and feed it into the second function to get something else out. Now, the ordered pair definition is a little tricky. I think there's a very good chance I write this down and actually make a mistake or blank it. So I'll start writing, and if it doesn't quite work, it doesn't matter. It's not really going to help you understand, but this down here will. So F or G, okay. So this would be the set of, so the inputs would live in X, and the outputs would live in Z. So it'll be of those such that, so X has to be in X, Z has to be in Z, and there exists Y in Y such that G of X is equal to Y and F of Y is equal to Z. I think that's not even that's even harder than it's supposed to be. So you put in X and you get out Z from this function if you put an X into G and you get out Y, and that same Y gets sent to Z. So as I said, that's not easy, it's tricky. But the formula definition is a little bit easier. So F after G of X is equal to, so you take the input X and give it to the function G. So that's now an output. And now use that as an input to F. Okay, so that would be slightly easier. And then the arrow diagram is probably easier again. So we have X. That's the set X, set Y, and the set Z. X, Y, and Z. And we have the function first G and then F. So this is where the language F after G. So do G first and then after that do F. So you take your input X, that'll get sent to Y, and then Y gets sent to Z. Well, we'll write down some other things. So the Y is equal to G of X. And then what this gets sent to will be called F of Y, which is the same as F of G of X. But the basic idea should be here. So take an input X, give it to G, produce an output, and then actually just we might as well put in terms of this notation here, this is the same as Z. And then you got that output from G, and then feed that into F as a new input. So you're applying functions in a chain. And indeed, for those of you who did higher level maths, you would have learned about the chain rule, and that's about differentiating compositions. So the function that takes in X and finally produces F of G of X is the function F after G. Okay, so as I said, a composition can be represented by a chain of arrow diagrams like this, one after the other. For example, let's look at the composition of x sent to x squared and x sent to 3x. We can represent it something like this. So let's draw an arrow diagram. This here, that can be our first real numbers, second set of real numbers, and third set of real numbers, because these are all reals to reals, reals to reals. So real numbers, real numbers, real numbers. So let's give maybe, consider 4 outputs. So we're gonna, our inputs, let's put in 0, let's put in 1, let's put in 2, And then let's put in an x, a general x. This is more for algebra, but we'll look at it now. Okay, so map these. We probably should have put in a -1 as well. There, we'll throw it in there. Okay, so first you do G. So G, oh, this is G after F, so it's the other way around. So we're going to do F first. So F first, X, the input is sent to 3 times that number. So -1 will be sent to -3, 3 times -1, which is -3. 0 is sent to 3 times 0, which is 0. 1 is sent to 3 times 1, which is 3. I'm going to forget about 2 just for space reasons. And finally, x is sent to 3 times x. Just that. So this is, we're applying the function first f. So we have -1 is sent to by f. So x sends an input to 3 times that number. So -1 gets sent to -3. 0 gets sent to 0. 1 gets sent to 3. And x gets sent to 3x. Okay. And now let's apply the function g, which is the squaring function. So I'm going to need eventually anyway 9, 0, and then 3x squared. So what are we doing? We're taking these outputs from f, just a selection of them, and we're applying the function g, which is the squaring function. So -3 squared is -3 by -3 is +9. And then 0 squared is 0. 3 squared is 9. So you can see this composition is not 1-to-1 because -1 and 1 eventually are sent to 9. And then 3x is sent to 3x squared. And so the function that goes from here to here is g after f. And we actually even have a formula for it. G after f of x is equal to 3x squared, which would be, we'll just leave it as 3x squared for now. When we have some algebra, we can simplify that a little bit. Okay. If you have a bijective function, so that's a function that's 1-to-1 and onto, then it has an inverse. So let's explain what that's about. The ordered pairs are just the flips of the ordered pairs. So consider the bijective function here. Let's say for argument's sake, so it's from x to y. I think what we'll do is we'll write down here. Yeah, let's say it's from 1, 2, 3, 4 to 1, 2, 3, 4. So let's send 1 to 3. Let's send 2 to 4. Let's send 3 to 1. And let's send 4 to 2. Oh, that's not what I want to do. So let's send 3 to 2 and finally 4 to 1. So this function is 1-to-1 and onto. Now we'll see with the arrow diagram in a moment. But we'll see with the arrow diagram in a moment. But we'll just look at it here. So does every output, does any output appear twice? 1 once, 2 once, 3 once, 4 once. So that means that it's 1-to-1. And is it onto is 1, 2, 3, 4 hit? Yeah, 1, 2, 3, 4. So it's 1-to-1 and onto. It is bijective, so it's invertible. And the inverse, you just flip these around. So you can have 3 is sent to 1, so you flip that around. 4 is sent to 2. 2 is sent to 3. And 1 is sent to 4. Okay. We're going to see, I think down later on, we'll see issues with if it isn't 1-to-1 or if it isn't onto, that you can't get an inverse. So the inverse, we can represent it a backwards arrow, and we'll do 2 different ways. So one is like this. So here's x, 1, 2, 3, 4, y, which is the same thing. I'm just going to call that x as well. Okay, so I had 1, 2, 3, 4. 1, 2, 3, 4. And I'm going to have f going this way. and I'm going to have F inverse going backwards. So it'll just be a backwards arrow. So F sent 1 to 3. No, it'll just be the tip of it, would be the thing. 2 is sent to 4. 3 is sent to 2. And 4 is sent to 1. And so the inverse, you just reverse the arrow. So 1 goes back to 4. 2 goes back to 3. 4 goes back to 2. And finally 3 goes back to 1. So it's just flipping it around. We can also show that if you do the composition of a function and its inverse, there's another thing which says that if you do F inverse inverse, so the inverse of F inverse, we might just point out that the inverse function is onto, because 1, 2, 3, 4 hit, and also it's 1-to-1 because you don't see 1 hit twice or 2 hit twice or 3 hit twice. So the F inverse itself is invertible, and if we flip these around, what do you get? But you get the original thing. So the inverse of the inverse is the original function. So what I'm going to say down here is if you compose a function with its inverse, it doesn't matter what order you do it in, it'll ultimately end up kind of being the same thing. So let's take, so this is a different picture. 1, 2, 3, 4. I'm just going to write the 4 dots. I don't quite have space to write in the numbers. So it'll be 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And we're going to, no, maybe I will label the sets because I'm trying to say that's important. And let's do F first and then F inverse. Okay, so in F, 1 is sent to 3, 2 is sent to 4, 3 is sent to 2, and finally 4 is sent to 1. And now let's do F inverse. So 3 is sent to 1, 4 is sent to 2, 2 is sent to 3, and 1 is sent to 4. And now this function that goes from here to here is F inverse after F. And what's this the same as? Okay, what was 1 sent to? By this function. So first 1 is sent to 3 and then back to 1. So overall 1 is sent to 1. Okay. Then 2 is sent to 4, sent to 2. So 2 ultimately is sent to 2. Similarly 3 is sent to 3 and 4 is sent to 4. So this is called, and I think we'll look at it on the next page, the identity function. So if you do F after F inverse, or F in the same way, same kind of as doing nothing. Because you kind of end up back where you started. So it undoes it. F inverse undoes F. Okay. Now what we should talk about now is that if the function is not onto, is it invertible? And if the function is not 1-to-1, is it invertible? We'll argue this by way of an example, 2 examples. So first we'll look at something that's not 1-to-1, and then we'll look at something that's not onto. So for the thing that's not 1-to-1, let's take set containing 1, 2, 3, set containing 1, 2, 3. Because remember, the inverse, if the function is bijective, just means putting the arrows the other way. So suppose I have a function that does this. 1 is sent to 3, 2 is sent to 1, and say 3 is sent to 3. Now if I do the inverse function here, if I do, well, strictly speaking, I can say the inverse relation, go back the other way, I've got 2 problems. So if you're going this way, 2 has no output. If you're going backwards, that's an issue, which we'll talk about. Well, that's not the one we're going to be concerned with, although actually both of them are covered here in this same one. And here you see that this, if you're considering 3 as an input for the inverse, it's got 2 outputs, but a function, every input is only 1 output. So this has no output, and this has more than one output. So this means if it's not onto, that means something's not hit. That means that elements not hit have no output. A good example of this is if we went back and looked at from real numbers to real numbers squaring. So if you would think, oh, the inverse is the square root, but because -1 isn't hit, we don't have the square root of -1, not in the real numbers anyway. And then the similar story here. So this is a kind of scenario where you have two different numbers sent there. So so something hit twice, not 1 to 1. Look, it's kind of clear. Just if you run it backwards, it's an issue. So you need them. If you want to invert a function, it has to be onto and 1 to 1. If it is, it's bijective and it's invertible. We would have said once upon a time that a bijection like this one, which is 1 to 1, it hits everything once and it hits everything. So it's a bijection that is like a perfect matching. So you got this matching between 1 and 3, and so you can turn it around the other way. Okay. So both of these, turning this around leads to non-functions. Okay. You have to be 1 to 1, 1 to. So any set has the identity function consisting of the ordered pairs. Every element is sent to itself. Okay. Equivalently, you can write it like this. If f is invertible, this is what we were looking at on the previous page. If you do a function f and then apply the inverse, you get the identity on x. Okay. So this is pretty much just this picture here. Do a function and then its inverse, you just go back to where you started. So overall you do nothing. And doing nothing where the input is equal to the output is the identity function. And here's a question that we considered as well. What's the inverse of this? The inverse is equal to f. So we argued this here. Like if you flip once to get the inverse, and then flip again, you go back to your original function. So the inverse of the inverse of the original function. And that means that if you do, so if we write this formula for f inverse, you'd get f inverse after f inverse would be equal to, now this should be the identity on y. But this f inverse is just f, so you get f after f inverse is equal to the if. So what this means is that they come in pairs. So inverses come in pairs, f and f inverse, and this is the inverse of that, and that's the inverse of that. And so if you do one, apply one, and then compose it with the other one, you end up doing nothing. So by the horizontal line test, a function is a bijection. It's a bijection if every horizontal line cuts the graph exactly once, in which case f is invertible and the graph of f invertible. Okay, that bit's a bit too tricky. Now here's a small thing, like we kind of messed around earlier where we just changed the domain. And what you can do is, say for student numbers, like you can go backwards from student number with the ID function. Remember, the ID goes from students to student numbers. So we have ID student to student number. Now, the way we set it up in the previous lecture was n was the set, or Cartesian product d, which is the digits 0 to 9, 8 copies of that. But not all, like this is a very big set, like or 1, 2, 3, 4, 5, 6, 7, 8 isn't a student number. And so this function isn't onto, so it's not invertible. But of course you still want to be able to take a student number and from it identify the student. So what we can say here, and I think we're going to draw a picture, is one-to-one functions are invertible on their domain. Now it's not a big deal in this module, but I think if we're down the line, As long as you have a one-to-one function, you can kind of invert it on its range. Now this remark here is just going on about, that's not too important for us. So this function is one-to-one, yes. So what you can do is you can do what's called a left inverse. So you can go from the range of the ID numbers. So that's all the, I would say, assigned. So these are all the ID numbers that are hit. So there's loads of there's loads of things in this set. It's like there's 10 to, is it like 100 million student numbers? There's obviously not that many students. So just look at the small subset of that, of assigned student numbers. And we can invert there. So if you do take a student, look at their ID, and then take this function that identifies a two-student number, the student is what's called the left inverse. We'll draw it in terms of a picture. So, so we're going to do this. I'm going to do something a little bit different actually here. I think I'm going to say, we'll define an easier way is just to define ID from the set of students to the range of ID. So RN there means range. So this is a new function where I've changed. This used to be this this set n, the set of all possible, well, the place where the student numbers live. Let's just go to the assigned student numbers, and we get something like this. So we've got this tiny little, this is the range of the ID function. These are all the assigned ones, and then we've got more numbers. So this would be the set n. Now you'd be doing, a lot of you doing without. So all the possible student numbers without the ones that were assigned. So these are the unassigned student numbers. Now, of course, you see, you don't really want to do this, do you? Because maybe next year there's more student numbers, or I could write it as, you could do maybe the complement. If you think of the, yeah, that would actually work even better. So this is the complement, so the not. Okay, I'm just saying all the things that are not assigned. So this here is the set n, and we have the function ID, which goes from the set of students. But you see, they all go in here. You know what I mean? It hits all of them. And what you can do is, rather than, so that's ID. So that's the full thing. It's not onto. It is one-to-one, but it's not onto. But what you can do is you can restrict from that you just go into here. So for the purposes of this ID dashed, the inputs are the same, but the output set is just this. So ID dash just goes here. And so what you have is that the ID dash, which just goes on to the assigned student numbers, hits every assigned student number, and then you've got your proper inverse. So this F that I'm talking about above really is the inverse of this, and what it basically means is you can associate to every student number a student uniquely. Okay, so you can say something like it's invertible on its range, but you see it doesn't go around the. Okay, so a one-to-one function is enough to identify objects uniquely. Probably spoke about that too much. Just saying about one-to-one, you can kind of invert them on their range. Here's another example of a function that is, it's not really a function, but the idea is this undoes this. But if you turn them around, whereas with normal functions, it works both ways, but these are only invertible on one side. So like this can't really be implied yet. It's kind of the idea. Something like that anyway. But here, this I want you to understand for the algebra later on. An inverse undoes the function. Okay, right, let's look at some questions. So let f be the function 0 is sent to 8, 1 is sent to 10, 2 is sent to 12, 3 is sent to 14, 4 is 16. And presumably, like when we write this, you have to assume that f is a function. And so the inputs are 0, 1, 2, 3, 4. Okay. So the domain is all the inputs. So the domain of f is equal to all the inputs 0, 1, 2, 3, 4. And then the range of f is all the things that are hit 8, 10, 12, 14, 16. We don't know the codomain, we don't know where they naturally live, that information isn't here. Okay, is this invertible? Ooh, so you could say, well, we don't know because we don't know is it onto. So there's a bit of an issue there. We have to assume really, and I suppose if someone really wrote down that, well, I don't know because I don't know the codomain, so you probably have to give them the marks because they really know what's going on. So basically what I'm getting at there is when we draw the arrow diagram, it's going to look invertible, but it assumes that the range and the codomain are the same thing. So we'll just assume for this one, assume that the codomain, the place where the outputs live of the function, is equal to the range of the function. Okay. So is f invertible? If yes, list the elements, otherwise explain your answer. So to see if something is invertible, what do? We recommend that you draw an arrow diagram. Okay, so let's do that. We're assuming that the codomain is the same as the range, otherwise it's not invertible. So let's look at the inputs 0 to 4. 0, 1, 2, 3, 4. This is, well, we can't name it because there's no name for it. And then over here, again, we're assuming that everything is hit. Okay, let's draw our picture. 0 is sent to 8, 1 is just in order, isn't it? 1 is sent to 10. We see this perfect matching. It's 1 to 1. It's on 2, yeah. So function. So we don't have two things going to one thing. It's two different things to two different things, and everything is hit if we make this assumption. So f is 1 to 1 and on 2, and therefore it's bijective. And if it's bijective, it's invertible. So is f invertible? Yes, it's invertible. List the elements of f inverse. Well, we just have to flip them around, don't we? That's all we have to do. We can look at it here if we want. 8 gets sent back to 0. 10 back to 1. 12 back to 2. 14 back to 3. 16 back to 4. Or else we can just flip the ones up there. Now I'm out of time to do the other question in this video.